Hey kids, in this lesson we're going to look at the relationship between functions, its first derivative and second derivative, and there's a lot going on here, and brilliant men have researched all this out and worked it all out, and it's totally fascinating how everything works. And what we're going to do is show a connection between all of these derivatives in the graph of the function, the original function. So what we're going to do is we're going to first start with what's called a first derivative test. And that's when you take a derivative of a function, set that derivative equal to 0, and determine where that function is equal to 0 or where it's undefined, where the derivative is equal to 0 or undefined. And once you find those specific values of x where the derivative is either 0 or undefined, then we've got what are called critical points. And a critical point is used to locate the specific places that the graph has all the different things that are going to happen to it, like a max, a min, maybe it doesn't have any extrema, and maybe we're looking specifically at a right or left endpoint. And so here's what we're going to do. You have a local maximum if the derivative, you're trucking along and the derivative goes from being greater than 0 to being less than 0. Okay? Why? Because think about this. We learned in the previous section, if the derivative is greater than 0, your original function is increasing. When the derivative is less than 0, your original function is decreasing. So what happens at this point right here? We have a max. Okay? What about a local minimum? Hey, guess what? You're going to go start off with derivative being less than 0, and then you're going to switch, and your derivative is going to become greater than 0. So just like what we just looked at, except in reverse. We're going to first be going down, then we're going to be going up. Okay. Hey, what happens if you have no extrema? Maybe your derivative does something like it goes from greater than 0 at a specific point, and then it goes, oh, whoops, greater than 0. Or you could be trucking along and your derivative might be less than 0, and then it goes to, oh, less than 0. So if something like this happens, then you don't have any extreme at all. On your left endpoint, we're looking at whether it is going to be less than 0 or greater than 0. So um, if the function is less than 0, well, we might have to look at some examples here. So what I'll do is I'll just say use your visual cues on left and right endpoint. Okay, use your visual cues when you graph this, and um, we'll check this as well. But keep in mind that if we're increasing, we're going to be greater than 0. So if we start at a specific point and start to increase, then that would be a minimum. And if we start at a specific point and then decrease, that would be a maximum. So use your visual cues on the left and right endpoints. But we would be able to tell, for example, if we come back up to what I've already drawn, if I start at my left endpoint and go up and increase from that endpoint, I have a minimum. And if I start at my endpoint and go down, I'm going to have a maximum. Okay. So we're going to find the extreme values of the following functions. We want to find the extreme values. So what are we going to do? We're going to look for derivative. F prime of x is equal to 3x squared minus 12, and we're going to set that equal to 0. And when we solve this out, we're going to get that 3x squared is equal to 12, so x squared is equal to 4, so x is equal to plus or minus 2. That's my critical points. Those are my critical points when x is plus 2 or when x is minus 2. That's going to tell me what's going on. So how can I sort this out? Well, let's create a little sign chart here. And we're going to look just at the derivative, and sign charts are really fun. We're going to look at, let's see here, will that factor at all? I don't know if that'll factor. We'll look at -2 and 2, and we want to know, what's going on with the different signs here. So when I've got 3x squared minus 12, if I put a number, and I just need the sign on this, if I put a number in, like, say, -5, just something way over here further to the left of -2. If I put a -5 in there, I'm going to get a positive value out. Okay, positive value. That means that my derivative is increasing at that point. And then I'm going to put in something like a number from in between -2 and 2, something like 0. When I put a 0 in here for x, when I put a 0 in here for x, I get 3 times 0 minus 12. That's going to be negative. And I don't care exactly what the number is. I just want to know what's the sign, the S-I-G-N. What if I pick a number like 7? What if I put 7 in, a number from this side of the number line? Put 7 right here in for x. And when we do that, we're going to get a value that's going to be positive because we're looking at 7 squared, 3 times 7 squared. So here's what's happening. My graph increases, decreases, increases again. So what can I know about this? Well, I know that that I'm going to have a max when x equals -2. And I know that I'm going to have a min when x equals +2. That's how that's going to roll. So I can use that derivative and that first derivative test to find these critical points. Okay, so take a pause for a second, or maybe, hey, I tell you what, why don't you try x squared minus 3 times e to the x. Pause the video, try it, and when you unpause the video, I will be working it out for you. Okay, so I'm going to go ahead and work this g to the x guy out. So I've got room right over here, okay? And so the first thing I need to do is find derivative. And in order to find derivative of this guy, we got to remember that we've got the product rule going on here. So if g prime of x, then what I've got is the first, x squared minus 3, times the derivative of the second, which is e to the x, plus the derivative of the first, which is going to be 2x times the second, which is e to the x. I'm going to set that equal to 0. And to solve this out, I'm going to, let's see, will anything work here? I don't know. I've got x squared e to the x minus 3 plus, minus 3 e to the x plus 2x e to the x, and all of that equals 0. And I've got e to the x in everything here. So what I'm going to do is I'm going to factor out e to the x, and that's going to get me x squared minus, let's see, let's organize it, plus 2x minus 3. I think that's what it's going to end up being. Let me just double check e. Okay, that's it. And what I can do now is I can set each piece equal to 0. So I can set e to the x equal to 0, and then I can set x squared plus 2x minus 3 equal 0. And what that's going to do is it's going to give me the things to work with on this. Now, e to the x will never equal 0 ever because e to the x is always above the x-axis, so it never actually crosses the x-axis. We don't even have a place where it's where this guy is undefined, so we can't really use that spot. But what I can do though is I can factor out my bottom, and when I do that, I end up with x plus 3, x minus 1. Okay, so when I factor out the bottom, I get x plus 3, x minus 1. And notice that's going to give me a 2x in the middle. So I've got a 0 at -3 and a 0 at 1. And what I want to do now is I want to check with these values the sign. I don't care what the value is. I just want to know what the sign is. And we'll check with e to the x because we're looking at the derivative. We'll check e to the x. We'll check x plus 3. And we'll check x minus 1. We're going to check each one of these different pieces. So when I put a number like -3 in, okay, I can't use that, it's going to give me 0. So I'm going to use -4. When I put a -4 in for x, I'm going to get a positive value with e to the x. When I put -4 into x plus 3, I get a negative value because it's going to be -1. And when I put -4 into x minus 1, I get a negative value. And so if I do a positive times a negative times a negative, okay, then this whole side right here is going to be positive. So if you multiply all these guys together down here, this will give you a ginormous plus. Okay, the whole derivative in this part is going to be positive. Okay, well, let's look at the next one. So if I take a number from inside here, say 0, okay, then when I put 0 in for x, I'm going to get a plus because, again, e to the x never crosses the x-axis. When I put 0 in for x plus 3, that gets me a positive 3, so that's also a plus. And then when I put 0 in for x on this last one, x minus 1, that gives me a negative sign. So a positive times a negative, that is a big old ginormous negative. So this middle guy then, the derivative is negative right here. Okay. Lastly, if I pick a number bigger than 1, say 5 or 2, when I put it in for e to the x, that's definitely positive now. We're growing exponentially. When I put 5 plus 3, that's positive, that's 8. And when I put 5 minus 1, that's positive, that's 4. Okay, so this whole guy is positive, and what that tells us then is this whole part is going to be positive. So when we look at this problem right here, and we're trying to find extreme values, if we were to graph that, we have a positive slope, positive, then we have a negative slope, negative, then we have positive again. So if I go from positive to negative, that's going to get me a maximum. When I go from negative to positive, that's going to get me a minimum. So we would say for this problem right here, I'm running out of room, we have a maximum when x equals -3, and we have a minimum when x equals 1. And I don't have my graphing calculator super handy right now, but we can find those y values. If you want to know a y value, you just plug in the -3 for x here and -3 for x here. It will give you a y value. Let me see if I see it. 2.99. So, and then the minimum when x is equal to 1, it would be negative 5.437. So here's your max and min values. And if I didn't list with the y coordinates earlier for this guy, you can find those out. Go ahead and practice that right now on your own.